In this video, I will walk you through free response question number 1 from the 2015 AP Calculus exam. This problem is a rate in, rate out problem, and it is calculator active, so we will use our graphing calculator as needed. Here's the number one thing you need to know in order to understand this problem. The definite integral of a rate from A to B is equal to the change in the amount from A to B. For example, if we have a function that gives the rate at which water flows through a pipe in cubic feet per hour, the integral of that rate from A to B will equal the amount of water that flows through the pipe from time A to time B in cubic feet. The rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is equal to 20 times the sine of t squared over 35. Cubic feet per hour. T is measured in hours, from 0 to 8. The pipe is partially blocked, allowing water to drain out of the other end of the pipe at a rate modeled by d of t equaling this expression, in cubic feet per hour, for the time from 0 to 8. There are 30 cubic feet of water in the pipe at time t equals 0. Part A. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval from 0 to 8? I think of this as a rate in, rate out problem because we are given a function for the rate at which water flows into the pipe and another function for the rate at which water flows out of the pipe. Let's enter each of these functions into the calculator right from the start. I like to always put the rate in as y1, and I put the rate out as y2. So hit the y equals button and type in each of the functions that we are given. Of course, you'll have to use an x instead of a t. At the beginning, I told you the main thing you needed to know is that the definite integral from A to B of a rate will give you the change in the amount of something from time A to time B. In this case, we need to know the amount of water flowing into the pipe during this interval. So if we integrate the rate in from 0 to 8, that will give us the number of cubic feet of water that flow into the pipe from time t equals 0 to t equals 8 hours. And this is something that we can just type into the calculator. So go to a blank screen, second quit. To integrate, we will hit Math 9. We are integrating from 0 to 8. And we want to integrate the rate in, r, which we typed into y1. To access y1, we hit the vars button, switch over to yvars and hit enter for function, and pick y1. So this is the definite integral of r from 0 to 8. And put dx and hit enter. So this is it, 76.570. 76.570 cubic feet of water flows into the pipe from t equals 0 hours to t equals 8 hours. Part B is the amount of water in the pipe increasing or decreasing at time t equals 3 hours. Give a reason for your answer. If you want to know if the amount of water in the pipe is increasing or decreasing at a particular time, all you need to do is compare the rate in with the rate out. If the rate in is greater than the rate out, then the amount of water in the pipe will be increasing. That makes sense. If water is flowing in faster than it's draining out, then water in the pipe will be building up. Similarly, if the rate in is less than the rate out, then the amount of water in the pipe will be decreasing. The rate of water flowing into the pipe at time t equals 3 hours will be given by r at 3. Similarly, the rate out will be given by d at 3. We can use the calculator to easily find both of these. Just remember that we put function r into y1 and function d into y2. I always put the rate in as y1 and the rate out as y2, so I don't get confused. In order to find r at 3 and d at 3, I need you to change one setting on your calculator. Hit second window to access the table setup menu. On your calculator, auto is probably highlighted. So go down and switch over to ask and hit enter. In this mode, if you hit second graph to access the table, the calculator will evaluate both of the functions that we have typed into y1 and y2 at whatever value we type in for x. So if we want to find r at 3 and d at 3, all we have to do is type in 3. So this is it. At time t equals 3 hours, water is flowing into the pipe at a rate of 5.086 cubic feet per hour, and water is flowing out of the pipe at a rate of 5.4 cubic feet per hour. So we see that the rate in is less than the rate out. Therefore, the amount of water in the pipe is decreasing. In other words, the amount of water in the pipe at t equals 3 hours is decreasing because r at 3 is less than d at 3. Notice that to help us understand the problem, I speak in terms of rate in versus rate out. But when I write my final justification, I don't mention rate in or rate out. That's because these terms are not specific enough for the College Board. So instead, just say r at 3 is less than d at 3. Part C. At what time t on the interval from 0 to 8 is the amount of water in the pipe at a minimum? Justify your answer. As soon as you see the word minimum, you should be thinking, I'm about to do a candidates test. To do the candidates test, we will need to find the critical values. You know how when we are trying to find the max or min of f of x, we find the critical values by setting f prime equal to 0. For this problem, we are trying to find the minimum value for the amount of water in the pipe. However, we don't have a function name like f of x, but in some way we still need to find the derivative of this function, the derivative of the amount of water. So let's just think of it as the rate of change of the amount of water. Okay, we're just going to put rate instead of derivative. But still, the critical values will be where the rate is equal to 0. For a rate in, rate out problem, the overall rate is always equal to the rate in minus the rate out. So, setting the rate equal to 0 becomes rate in minus rate out equals 0. We have functions for each of these. So the rate in is r of t, and the rate out is d of t. So r of t minus d of t equals 0. This will give us the critical values. However, it'll be slightly easier if we add d of t to both sides and turn the equation into r of t equals d of t. In other words, the critical values will be the values of t where the rate in is equal to the rate out. We can use the calculator to find these values. Remember that we have typed function r into y1, and we've typed function d into y2. We need to find where function r equals function d. In other words, we need to find the intersection point between the two functions. Before we hit graph and start looking for intersection points, we need to adjust the window. So hit the window button. How will I adjust the x min and the x max? We're going to use the endpoints of the interval as x min and x max. So 0 and 8. So x min should be 0 and x max will be 8. Now, what about y min and y max? The most important number is the Y max. We need the window to be big enough to see the values. Looking back at part B gives us an idea of the size of these rates. R at 3 was 5 point something, and so was D at 3. So the only values we've seen so far were less than 10. So a Y max of 10 is probably fine. These values are not going to be negative. So we could make this 0. I think I will leave it at -5. I just like to see a little bit of space below the x-axis so I can just clearly see what's going on. But we can always adjust this later. Let's go ahead and hit graph and see what we've got. Kabam! So we need to see the intersection points, and I can see some here and here. I think I would like to increase the window just in case there are any other intersection points. So I'm going to make that Y max a little bit bigger. Okay, let's make it, let's say 30. Okay, so now it's curving back down. So I can clearly see that there are no other intersection points on this interval. I'm seeing the whole thing. So, what are these intersection points? Let's hit second trace, and option 5 is intersection. Move the pointer close to the point of intersection and hit enter 3 times. Enter, enter, enter. So, the first critical value is 3.272 if you round. Let's store this value into a letter on the calculator. So hit second mode to quit, type X, and then type the store button. I want to store this value into the letter A. So alpha A. This way, if I need this value later, which I believe I will, I can just type A instead of typing in all of these decimals. To be clear, if you don't use this shortcut and store the value into a letter, when it's time to use this value, you have to use all of these decimals. Go ahead and record that first critical value in your work. Now, back to the calculator, and let's see if we can find a second critical value. Second trace, option 5 for intersection, and it looks like there's another intersection point over here very close to 0. So I'm actually going to move a little bit past it so I can clearly see it, and I'm going to hit enter 3 times. Enter, enter, enter. So this intersection point is 0. 0 is included in this interval, so technically we have a second critical value at t equals 0. However, we were going to put endpoints on the candidates test anyway. So let's get to it. The first value of t will be the first endpoint of 0, and this is included, so I will put it in a bracket. Next, I will include my critical value of 3.272, so 3.272. And my final value of t is the other endpoint, which is 8. Bracket. Looking back at the setup, remember that there are 30 cubic feet of water in the pipe at time t equals 0. So that's the initial condition. So that's easy. I can immediately just write down 30 as the amount of water at time t equals 0. But what about the amount of water at time t equals 3.272? I'm going to have to start with the initial amount of water, 30 cubic feet, at time t equals 0. And then I need to add the amount of water that entered the pipe from time 0 to time 3.272. So that'll be the integral of the rate in, which is r of t. So this expression represents the amount of water that entered the pipe. Of course, we must subtract the amount of water that left the pipe. So, using that same integral from 0 to 3.272, and the rate out is given by function d. So again, what I'm doing is the amount of water in the pipe at time 3.272 will be the initial amount of water in the pipe plus the amount of water that came in minus the amount of water that went out. Notice that the limits of integration are identical. When that is the case, you don't actually have to write it as two separate integrals. It will save you some time if you rewrite this as a single integral. And this is something we can type into the calculator. Just remember that function r is in y1 and function d is in y2. So I'm going to start by writing 30 plus the integral from 0 to this value, which I typed into letter A. So to the calculator, we will hit 30 plus math 9, integrating from 0 to A. So alpha A. And here comes the rate in, which is y1, so vars, y-vars, function y1, minus the rate out, which is y2. And that's it. 27.964 or 27.965 if you like to round. In a similar way, we can find the amount of water in the pipe at time t equals 8. Again, it's going to be the initial amount of 30 cubic feet plus the change in amount from 0 to 8, which is going to be the integral of the rate in minus the rate out. So we will just put this into the calculator. We can save a tiny bit of time if we just go up to the expression that we typed in before and hit enter. It duplicates it. Now I can just go back in and instead of the A, I can just type an 8. A little bit of a time saver. So we have 48.544 if you like to round. Notice that we are not being asked what the minimum amount of water is. We are just asked at what time the amount of water is at a minimum. So the amount of water in the pipe is at a minimum at time t equals 3.272 hours. Justify your answer. My justification is see candidate's test. Part D. The pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve, an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. The first sentence says the pipe can hold 50 cubic feet of water. So the pipe will begin to overflow when the amount of water in the pipe is equal to 50 cubic feet. We just need to write an expression for the amount of water in the pipe. The amount of water in the pipe will equal the initial amount plus the change in the amount of water in the pipe. But this is a rate in, rate out problem. So instead of just saying the change in amount, let's say the amount in minus the amount out. We know that the initial amount of water in the pipe was 30 cubic feet at time t equals 0. The amount of water that entered the pipe will be the integral of the rate in from time t equals 0 to this unknown time w. We're trying to find the time when the pipe will overflow, and we are supposed to call that time w. So instead of putting a number here, we'll just put the variable w. So this is an expression for the amount of water coming into the pipe. Now we subtract the amount of water that flows out of the pipe from time 0 to the mysterious time w. And of course for that, we will integrate the rate out, d of t. So this is a valid answer. You could also write this difference as a single integral. So here is another valid answer. Or subtracting 30 from both sides. Here's another valid answer.